So for you guys who don't know me, I'm Fernando. I'm the executive assistant and actually communications director of the System Dynamics Society. And today I'm just here for an as an intermediate person. This seminar is from our special interest group from the pre-college education. And I hope by the end of this discussion, you learn a little bit about different experiences with pre-college education. And if you're not familiar with the benefits of being a member of the System Dynamics Society, or you are a member of the System Dynamics Society and looking forward to renew your membership, I remember that you get free access to all seminar series. This one is free, but there are upcoming ones that are usually you pay a small fee, but as a member, you get this as a benefit. You get free discount on our 2022 conference. Here says 2021, but it's actually 2022. We're meeting in Frankfurt next year in person, finally. You get full access to our scientific journal, the System Dynamics Review, exclusive prices on our bookshop, free access to our networking series. And if you're planning to learn more system dynamics, you get access to a pool of mentors that can help you develop those skills. This is just a shout out for all society sponsors, and it's only through their help that we're continuing being able to expand the system dynamics field and get the word of this amazing approach out there. A reminder that we have an upcoming webinar, the first of the year in January. It's Dancing with Systems, Moves for Turbulent Times with Marta Serone. She's from the Academy for Systems Change, and she's gonna present us a little bit of and review the work of Dana Meadows. It's a really great opportunity to learn more about Dana Meadows' work. Just briefly introducing the speakers of today. We have Sistem. She's going to start with her presentations very soon. And then Ozgun and Senna. Garkan is not here, but he's here maybe. He's going to be part of this presentation with Senna. And a quick agenda. We have a presentation, 3 presentations, 45 minutes, starting with preschoolers as systems thinkers, testing the water, then going to understanding composting with systems thinking, and moving forward with teaching energy conservation, and household waste with systems thinking approach. And right after these 3 presentations, there's a SIG meeting. So for discussion and questions that you guys may have for the presenters, you can keep them and actually approach the presenters right after the presentations. I think that's all from my side. We keep kicking off with Sistem, and I'm going to stop sharing my screen. Thank you so much.
Thank you, Fernando. Greetings, good evening, good morning, good afternoon. It's evening in Turkey. I'm from Turkey. My name is Şebnem Feriver, and I'm going to present my career in a short way. I have a dual career. I'm an early childhood education researcher. I do my research as an independent researcher, and also I have a career in social development projects. I, at the moment, work for a project that is mainly focusing on refugees, Syrian refugees in Turkey. Now I'm going to provide you some background about my research that will be showed very soon. So the main idea of the project came from my doctorate research. I was very interested in systems thinking because of my special interest in education for sustainability. They are all very related. And I realized that many scholars in the field were saying that young children are natural systems thinkers. Since I'm from the early childhood education field, I questioned this claim because I know the developmental characteristics of those young children. During my doctorate research, I worked with preschoolers from different educational contexts both in Turkey and Germany. I worked with children from 5 different contexts, and data derived from this attempt showed that actually we cannot obviously claim that young children are systems thinkers. So I had another questions, of course, and I asked those questions like, is it possible to support young children so that they can become systems thinkers in time? And what kind of learning content can support their systems thinking skills? And how can we measure their skills so that we can reflect on the created learning contents? And the project that I'm going to present you guys is mainly about those questions. And now I'm going to share my screen and start my presentation. Okay. So the title of the project is Preschoolers as Systems Thinkers and Testing Water. So why this project? There is, I think, no need to explain systems thinking to this audience, but in a short way, I focus on systems thinking because of education for sustainability. It has a very good way, I mean, it has a very good background to support as education for sustainability skills of children. And this is why it has been now defined as a key skill in the field of education for sustainable development. And some of the resources specifically claim that education for sustainability or education for sustainable development cannot be approached without some systems thinking. So the main, sorry. Okay, I think, yeah, this is better. So the main aim of the project is to cement the link between systems thinking and education for sustainable development. And it presents an example of a systems education for young children by developing and implementing a learning framework created specifically on the theme of water for children aged 5 and 6, as well as measuring its impact. Okay. The content of the project is very related with the sustainable development goals, specifically with good health and well-being, quality education, clean water and sanitation, responsible consumption and production, as well as life below water. So what's new about this project? We introduced some novel elements in this project. Almost 200-page long systems education guidebook on water for early childhood education was created in line with the project-based learning, and it was developed by EST and ST experts and included 27 integrated play-based preschool learning activities on the theme of water, and also 2 specific systems education assessment instruments were developed for this age group. Shared story reading, interview protocol, and data analysis method were created by utilizing this very famous storybook, The Water Hole. And also a concept mapping, interview protocol, and data analysis method were created to explore and assess how preschoolers construct causalities around water-related concepts. Now you see some of the main subjects included in the systems education guidebook. There are some introduction pages about both sustainability and systems thinking, and also for early childhood education in the context of early childhood education, and also project-based learning. We claim that cognitively challenging questions can be as a kind of an important start point to include children into some cognitive, higher order cognitive processes. And also we created 27 learning activities, and also the book has some summary tables. Okay, this project included a lot of good spirit people. We were 3 researchers in the project. There were 32 children, and also 2 preschool teachers and 1 trainee teacher was in the process, and also 2 senior systems thinking trainers guided us through the process. So how was the project carried out? There are lots of things in this slide. I'm going to briefly present them. So first we started with pre-test, then we had this implementation, and then we had post-test, and we had this impact analysis. And the project continued for 4 full weeks, 3 days for pre-test, 14 implementations, and then 3 days for post-test. Okay. So children's drawings are considered as an effective tool for assessing the process. And in the middle of the process, we asked the children to draw what they have obtained from the learning experiences. And the main findings from the first drawing session indicated that children were able to incorporate a lot of elements related to water cycle, and they could conceptualize the continuous loop of the water cycle. And behavior of the water in our planet was demonstrated in the drawings by including some elements of evaporation, condensation, precipitation, and collection. And drawings of sun and underground water appeared most commonly in most of the drawings. And so we saw that more invisible components became visible components for children. In the second drawing session, we asked the same question. Draw what you have obtained from the learning experiences. This time, most of the children preferred to draw the play activity on the causal relationship between population growth and the freshwater resources. This play activity was inspired by a fish banks game, but we have this very simple version of it, and the theme is different actually. So we see behavior over time graphs in the drawings of children. These are the behavior over time graphs drawing of the child, and they were able to explain the behavior of exponential growth of populations and how they affect the distribution of shared resources. Behavior over time graphs and bar graphs were also created with the active participation of the children. The drawing on the right-hand side is a drawing of a child. On the left-hand side was created by me with the active participation of the children. So our learning experience put some emphasis on the hidden water footprints. We started the activity by asking children how much water might be used when making a pair of jeans, chocolate bar, plastic water flask, etc. And we implemented our activity, and at the end of the activity, we helped the children to construct bar graphs. So now I would like to present the end result of our project. While analyzing the narratives of the children, together with my dear friend Emre Göktepe, we created a stock flow diagram, which is a systems thinking tool. Now you see on the screen. This diagram was composed of the concepts and causality structures built by children. Actually, we created this diagram, but it was based on the narratives of the children. During both pre and post measurements. And the children's level of system elements and causality structure recognition levels are given in the next slide as a table. So the main elements that were written in the stock flow diagram are now here as a table. So you see pre-test and post-test frequencies of those systems elements, and we made a paired sample t-test to compare and contrast both pre and post measurements, and there was a statistical significant increase in the scores from pre-test to post-test. And also we made binary dice. This was also Emre's doing, binary analysis, and we saw the cluster distribution changed from pre-test to post-test dramatically. Okay, let me continue. Okay. As I told you before, we also made concept mapping exercise with children. As you can see from on the left-hand side, these are the same child's concept mapping exercises. On the left-hand side, we see the pre-test example. On the right-hand side, we see post-test example. On the left-hand side, we see three connections. Actually, as a researcher, we wrote those connections according to explanations of the child. On the right-hand side, we see 10 relevant connections created by the child. As a whole, for 29 children, this is the end result for concept mapping exercise. The thickness of the connecting lines on the map reflect the total frequencies. And if the line is thicker, then there's more frequency for this connection. And the blue bars on the lines demonstrate the results according to the pre and post test. And similar to the shared story reading results, both number and the levels of sophistication of the connections made by children increased from pre-test to post-test. All in all, the projects showed that the implementation of the project-based learning framework had a positive effect on the children, both in terms of their development of concepts and their ability to integrate concepts into a web of causal connections. So my main message for the researchers for early childhood education is there is hope. So I would like to thank the contributors listed on the slide. The scientific article of the project is recently published by Journal of Environmental Education Research. The cover of the guidebook is on the bottom left. Now I'm going to share you guys links to both of the resources, and I thank you for your attention. Thank you.
Thank you very much, Sistem. The next presentation is a recording by Özgün, a primary school teacher, and I will show her presentation, which has been pre-recorded. I cannot, 1 minute here. I will start it.
I am member of Systems Thinking Association, and today I will share my experience in how IB Primary Years program and Systems Thinking work together in the classroom. International Baccalaureate offers for high-quality, challenging educational programs to students aged from 3 to 19. The programs focus on fostering critical thinking and building problem-solving skills while encouraging diversity, international-mindedness, curiosity, and healthy appetite for learning and excellence. And primary years program for children aged 3 to 12 nurtures and develops young students as caring, active participants in a lifelong journey of learning. International Baccalaureate is an international program that we apply in our school. We also follow the national curriculum. There are primary years program objects that we should use in our lesson resolutely. We operate in 6 units throughout the year, and the key concepts guide us in the processing them. And we prepare our inquiry programs according to these themes. We aim to prepare an environment for students to become individuals with the specified profile features. It was meaningful for me to combine system thinking with the PYP curriculum because I can easily fit into my lessons and benefit from it. The important point here is to actually see similar aspects of both sides. And there are key concepts that complement each of the iceberg. We use these concepts to make understanding and questioning more visible. In fact, every concept has a question that bring us together with system thinking tools. For instance, key concept change match perfectly on patterns of behavior of the iceberg visual, or causation and connection on structure of system layer. And this is an inquiry cycle we use in our classroom. We hang a big poster of this inquiry cycle on the back wall of our class, and we follow the inquiry steps from here and post the activities we have done in each steps here. One of the good things here that the work we do using systems thinking tools has correspondence at every steps. And concepts idea came in connection with our team. It was a study I was thinking about and even wanted and try. I started planning with system thinking tools. A project that lasted 6 weeks was designed because that's all we have left until the school summer break. First of all, I did a pre-assessment to look at the children's perspective and previous learning, and I did this using a letter of inference. We wanted to see what children think about garbage. And everyone wrote the same situation under the letter. I see a bucket of garbage. And the result was not surprising. One student's assignment had the words, "I'm running from the garbage" in capital letters. And actually, what I wanted was to change this understanding. First, we read a book in the classroom about what compost is, and they prepared a compost booklet. Then we discussed whether we could do it. And I shared the stage of the project, and we started collecting garbage. At this stage, we collected a lot of waste from house and school cafeteria and started a build-up heap. The next step was the temperature of the heap every day and create appropriate conditions. And each student wrote the heap temperature on a table every day, and we created a behavior over time graph at the end. Dates indicated by an asterisk on which we observed certain states and activity, for example, watering, mixing on a heap. We wrote along a story to better explain these reasons for the change in the behavior in the graph. The temperature behavior of the heap on the story was very similar with what we observed in a real heap, and so students can make inferences about what's happening in the heap. A story has been prepared to help them understand better how the transformation in the soil goes. One of our high school students drew this beautiful picture of this story. For this story, we use system thinking tools to analyze the change in the soil. In the story, protagonist of the story, Ali, drinks a potion and becomes so small that he can see micro-creatures in the forest. He then meets the bacteria and gets information about the composting process, including temperature rise of the heap. And we made a behavior over time graph about the story, and at the same time we dreamed of our own heap. And it means that when the temperature was high, there were specific creatures, and there was an excitement about what will come in the classroom. Already in all garden times, most of the students were controlling the flies around the heap. After this story, they started to look for other living things, even the invisible ones. And before starting this slide, I must clarify one point, especially in meeting with many attendants having a strong system dynamic modeling background. I know the presentation here is another numerical model with a presentation. You should read the model as a proxy to stock flow diagram. This is a translational diagram for third graders to understand the concept. And we introduce living plant as an accumulation of carbon dioxide, water, minerals from soil, and solar energy from sun. While getting these as inflows, a living plant gives oxygen and water as an outflow. And I will present another slide soon that we developed to quantize photosynthesis as a very simple math exercise. But here we just say that a living tree is a net accumulation of these flows. And we introduce this living tree stock flow diagram to explain the heat outflow during composting process. This is how we do it. And if we change the inflows to outflows and outflows to inflows, then living plant stock becomes a dead plant stock. This is what happens during composting. Oxygen and water come in. That's why we try to keep the compost heap wet and mix it time to time. And carbon dioxide, water, soil, and energy comes out. And the temperature rise in the heap comes from this energy. That plant realizes energy that took from sun. We saw the vapor coming out of the heap. That is carbon dioxide and water. And the soil is the compost we are trying to get from the dead plant. We have created a stock flow diagram showing how the transformations occurs, and students realize how the dead plant comes back to life and becomes usable. And now I would like to show you photosynthesis using the same stocks and flows, but with adding very simple math. As these are primary school students and they have a couple of years for chemistry, they do not what atoms, elements, molecules are, but this shouldn't be a big obstacle for the depth and content we aim to deliver. And we give colors to molecule types and number of atoms information for the related molecules. Then we ask them to do the inflow-outflow calculations. There are two interesting points here. First is the accumulations. When they do the calculations, what they find is receipt for sugar. So they learn that basically a tree is made up of sugar. But how those molecules bond together? They come as separate entities. They see there is one more thing coming into the tree. This is energy from sun. And so we reverse the process, then stock flow diagram will be like this. Here it is easy to see what burning is. Burning is outflow of an energy that tree had stored for years. If it is very fast, we call it fire. If it is slower, we do not see the flames, but nevertheless, heat outflows. This is what happened in composting. And finally, we made a final assessment and using the same method. The results were really gratifying because everyone had the same thing written on the paper. I made compost. As a final step, we sent a letter to parents and asked them, does your children's aspect change about garbage? Did they do anything about compost at home? Many said that they were separating the garbage for compost, that this study was very useful. And our plan after obtaining compost was to do planned experiments, but we couldn't do it because we didn't have enough time. And growing seeds for each trial can be plotted at the time of plant growth rate. Growing seeds for each trial determine the average insemination and largely what you want yourself from the experiment. Your other experiments, which pot is the most suitable for the inseminations of our experimental children, which for the plant, which for the health. If we could do the experiments, for each experiment we will draw behavioral time graphs of seeding and plant growth. Then the graphs will be compared with each other to find the best soil mixture for seeding, for plant growth, and for plant health. But we didn't have enough time. So instead, we used the sack of soil we got from the compost for growing new plants on our school garden. They gave the plants planted with compost as a gift to their families on the day of their grandparents' day next year. And this activity was carrying out using systems thinking tools within the scope of PYP teams. In this sense, it has been observed that it is a very good guide for developing inquiry and problem-solving skills. And it was observed that the students found the subjects more enjoyable by using system thinking tools, and it was evaluated that this approach supports permanent learning. It has been shown through these activities that systems thinking can associate it with themes and outcomes of primary year's program of IB. And thank you for your attention.
Thank you. Now, can we please have Sena's presentation?
Okay. Hello, everyone. This is Sena. Thank you very much for joining us today. I'm a member of Systems Thinking Association in Turkey, and I worked as a science teacher in Darüşşafaka Middle School for the last 3 years. Now, currently, I'm living in Munich, and today I will present the studies we have done last year in Darüşşafaka. And actually, today I was going to have another colleague with me, but unfortunately, he had some health issues, and that's why he couldn't join this session. But I will do my best for covering up everything. So here you see the last year we had different applications with different grades, and all of the activities were based on the objectives in the national curriculum. So, and they were all after-school activities, which included volunteered teachers and students. And although many of the topics here included in the science objectives, we worked closely with mathematics, and we designed and taught all of the lessons together. Here you see that with 6th grade students, we studied motion in 1 dimension. We had a little introduction to Stella Online with piggy bank dynamics, and we solved some distance speed problems on the Stella Online website. With 8th grade students, we had reservoir dynamics. So it was including understanding the change in water reservoirs of Istanbul, and understanding the linear equation and solving problems related to it. And lastly, we had 2 studies with 7th grade students. The first one is energy conservation and the household waste, the second one. And today I'm going to explain them in detail later in my presentation. And I will start with the first one, energy conservation study. It included 2 states. The first one was the introduction to Stella Online with motion in 1 dimension. And the second one is included the concepts like force, displacement, work, and energy. And they were all based on the objectives from the national curriculum. So basically, we were expecting students to be able to explain that work done physically is related to first applied force and the displacement. And we were expecting them to associate energy with concept of work and classify the energy as kinetic and potential energy, and concluded that the energy is conserved, and they were doing it based on the conversion of kinetic and potential energy. We had 17 students volunteered to work on these concepts after the school, and they attended the lessons for 11 weeks. And here you see the first part, the introduction to Stella Online. To teach the basics of systems thinking and modeling, we chose a different topic than the energy conservation, but we wanted that topic to be somehow related to the energy conservation. That's why we started with motion in 1 dimension. And here we defined the position as a stock, and it can increase by time, or it can decrease in time. And we define the flow connecting to it, and namely it's like change in position. And we let students to build this model and explore how the change in the flow affects the stock. And here they also learned about the step function to write in the flow. And they try to describe like similar motions like here in the graphs. Sometimes we describe the motion in a paragraph, and we ask them to write an equation to the flow, and so that the position graph will match the described motion. And sometimes we gave them the graph and asked them to guess like what should the flow look like to have a motion like that. And from that point, we started to grow our model. So our intention, like the first intention, was to teach work done on an object. And this is related to the force acting on an object and the displacement of that specific object. And it is really easy to jump from here to the work done on an object. So basically, if we want a change in a position, what could be done? We should apply a force to that object. So if we apply the force, so that object can change its shape or its position as well. And now that we know the force, and also we know how much change in position is happening during that time, and if we multiply these two, then we will find the change in work and in a time unit. And in the end, this will show us the work done on an object. And here we had an opportunity to teach the concept of velocity as well, and its relation to the position of an object. Well, by definition, velocity is the rate of change of position with respect to time. And we can easily see that it's this flow here is equal to the velocity. But similar to the position, velocity can increase or decrease in time. So we showed it as a stock, and there's a flow connecting to it, and it is named as change in velocity. And this is depending on the force acting on an object and also mass of that specific object. So, and you see that the colors are different here. If we apply the same force to two different objects, the object with smaller mass will have higher velocity in the end. But this was not one of our objectives to teach the students, so we decided to give the numerical value 1 to mass here. So we continued like that. Here, understanding the velocity was also important to understand the kinetic energy later. So now we have a base of a model to continue with the energy conservation. Until that point, all of the students created that model and put numerical values, and they tried to solve problems. They saw the graphs, and based on the graphs, they changed some stuff inside. And so again, they build it all like every student. But from that point, we stopped building and we started explaining the model. So as I said, that we are ready to move to the kinetic energy and potential energy conversion. So from how can I explain it? The flow from potential energy to kinetic energy, or from kinetic energy to potential energy, is depending on the work done on the object. And it is just easy to see it that way. So when I'm doing a work on an object, the kinetic energy gain is equal to the work done on the object. And this conversion can be seen here. And it also works as a numerical value as well. So here, we only put the values for force, mass, and also the initial potential energy. And the rest are the results of the working system. And it's really beautiful because with these graphs, we were able to talk that what is the reason behind such a motion. So they were seeing that there's an increase in velocity and the result position is like that. But why is the velocity is increasing? It's because there's a net force acting on that object. And here they see that there is no change in velocity. And the explanation is there's no force, or the net force is 0. And they saw that there's a decrease in velocity. And the explanation is there is a force acting on that object, but in the negative direction to the motion. So it was really fruitful to talk about them when they were in the middle schoolers. And here they also saw that the work done on an object is like the same, the kinetic energy gained by that object. They saw it too in here. So I will show you some example worksheets here. They are not all of them, but some examples. So for example, here we just wrote a problem and asked them what could be the stock and what could be the flow for that problem. And based on that, they prepared a model. Here again, we had some problems related to the the physical work, and we built the model before together, and we asked them to rebuild it and then change some of the stuffs and try to see the change in the graph. And they were and we didn't give them the model settings, so they needed to find them by themselves here. It is this is also similar to that one. This was one of the exercises from the energy conversion. So we gave them the velocity time graph, and based on that, we gave them the model, and they answered some questions related to model, and they were also trying to explain the reason behind this velocity time graph. Yeah, I can share the examples later as well, no problem. And the second part, the household waste. This is also done with 7th grade students, and we were expecting students to examine recycling in terms of effective use of resources. This was also one of the objectives in National Science Curriculum. We had 26 students volunteered for the activities, and the duration was 5 weeks. We divided the students into 2 groups. 14 of them were facilitators, and the 12 of them were participants. And the facilitators were the one who attended the first cycle, the one in the energy conversation. So they were here to help their peers to understand systems thinking and in groups. This was the whole model we used in the class, but we started with it. Oh yeah, okay. We started with here, this part. We didn't give the whole model in the beginning. We just wanted them to explore the difference between waste and garbage, because in class we discussed it what is waste and what is garbage, but here we try to visualize to let them see it. So for example, there's a consumption happening here and there's something in the end, but this something can be 2 different things. If we are recycling it or if we are composting it, we can call it waste. But if we are not doing it, then it is useless, it's garbage. So we were asking students to understand the difference between waste and garbage. And after discussing this in the whole group, the rest of the model, this model, we played a game with students. It was like a taboo game, but a little bit different. So we gave them, but we didn't give them the whole model. We gave them just this part. So this is the explanation for the whole model. So this part explains everything, what is happening in here. And also we gave them a little part, this part, and an explanation for that. And we asked them to complete this model based on the explanation here. So we didn't give this, just this one. And they were trying to build the model based on what is written in here. And from the facilitators, we asked them to help their peers, but the taboo part is coming. They weren't allowed to tell anything written in here. No stocks, no flow. They weren't allowed to tell them unless their peers are saying them. So they were trying to help their friends, but they weren't allowed to tell anything from here, but they could just help from the explanation here. And every student group created a model similar to this one. And later on, we discussed everything in the whole group and completed the model all together. Thank you very much for your attention. this is the end of my presentation.